Hi, welcome to the last section of today's tutorial on recent advances in vision and language research. This last part focuses on some of the aspects of the vision language navigation problem that are highlighted and become more pronounced as we switch to more realistic environments. My name is Yoav Artzl, and I'll be presenting this part together with Peter Anderson from Google. So what have we done so far? So we started the first half of the day, we talked about vision and language understanding, including talking about the VQA problem. And in the second half of the day, we focused more on vision and language navigation, on problems sometimes often referred to as VLN. We introduced the problem, we talked about models that focus on generalization to unseen environments, and now we're focusing on some of the challenges that arise as we switch to more realistic scenarios. So what does realistic scenarios introduce into the problem that is not studied by current methods? So this is a panorama from the Matterport 3D dataset and environment that is commonly used in some of the most well-studied benchmarks in the field, including room-to-room and room-across-room. It's a relatively clean environment. These are pretty standard panoramas that are collected with the intent of marketing houses to potential buyers. These kind of environments, although they use real-life houses, they're actually very different from what agents are likely to encounter in the real world. For example, consider this scene that looks very different. This is a house with two children and a mother watching them as they unwrap gifts. It's a much more cluttered and complex and even more interesting environment. The positions of the objects and their configurations, the perspective of the image, they all introduce challenges that are not seen in the Matterport 3D data. Things become even more complex as we introduce agent movements, which provides these dynamic views with very high diversity of perspectives and partial views. For example, when the drone starts flying, it gets near to the table from this weird position that requires us to reason about the chairs by only seeing them from up close in a very partial way. As it flies into the living room, it encounters this weird structure on the left, which as we fly back into the house, we will notice is actually a cat play structure where cats climb on. Something that is very hard to reason about when we observe it from this partial view as we enter the living room. So these kind of environments are fundamentally different from what we see in Matterport 3D, and it's not just that they're more complex, it doesn't include more objects, but they're completely different. So more data of the same type is not going to help us solve this shift in the distribution of observations, and this visual divergence also leads to very different language. So in this part of the tutorial, we'll focus on three aspects of the problem that are highlighted by this transition to more realistic environments, and we'll do this through three case studies. I will present the first two, and Peter will present the third one. In the first one, we'll talk about real-life observations through the case study of urban navigation using the touchdown benchmark. In the second one, we'll talk about real-life control of a physical agent by talking about controlling a quadcopter drone for instruction following. And in the last part, we'll talk about how we can utilize this kind of reasoning that we learn in simulation in environments like Matterport in order to navigate in physical buildings. Okay, so let's start with the first part where we discussed real-life observations. For this part, we use the touchdown benchmark. It's a panorama-based vision and language navigation, or VLN benchmark, that also includes tasks for spatial reasoning in an urban environment. The focus of today is in touchdown are the task and data collection considerations, but I'll also show some baseline to give you an idea of a current state of the art on this task. Touchdown uses real observations at scale by using Google Street View panoramas of New York City. These environments are significantly more complex than what we see in Matterports. We see a large diversity of objects and different perspectives on them, a lot of clutter, and no uniform appearance or surfaces. So for example, here we can already see the crossing of the road to be extremely non-uniform and noisy, and a lot of movement when people and cars are moving around, often appearing between panoramas as the agent will move. Still, similar to Matterport 3D, it provides a relatively consistent point of view because of how this data is collected, and it's a panorama-based navigation, so it doesn't allow for the continuous control, which we'll see later on when we discuss the quadcopter drone. The touchdown environment includes almost 30,000 panoramas in a large area of Midtown and downtown Manhattan. These panoramas are connected between them using edges to create a navigation graph with around 60,000 edges, with a diversity of angles for transitions between the panoramas. This gives you about 120,000 states for a discrete navigation, significantly larger than any of the houses that you might encounter in an environment like Matterport 3D. The panoramic images are part of this street level environment, which you can go to the link here at the bottom right and request access to, and following a quick procedure, Google gives you access to download the environment. Task-focused navigation in this kind of environment is extremely challenging. There is actually a lot to describe in this kind of environments, and without a clear aim, what you notice is that instructors tend to become overly verbose and provide extremely descriptive language. Now, although this provides a very interesting and complex language, it's very unnatural, and in general, you don't really need to account for much of the language in order to to follow the navigation task successfully. So the solution to this that Touchdown adopts is to create more natural language that is more similar to how humans use language, is to adopt a solution that elicits language with a specific intent, creating a very specific task for navigation, and incentivizing instructor with a game-like dynamics that influences their pay. So for Touchdown, we crowdsourced data with a writing task where we ask to write instructions to follow a path and describe the location of an object that the instructor is hiding in some location at the end of the path. This really focused task makes the instruction more natural for the writers, and we also guide workers not to count intersection or not to use text and store names, so we can focus more on spatial descriptions. So the question, of course, is what do we hide? And the answer is that we hide a Touchdown, the Cornell mascot, and this is what gives this data set its name. So let's look at a very quick example of what the kind of instructions a navigation path that Touchdown includes. In this example, the instruction is that is included in part of the data set is orient yourself, so the umbrella to the right, go straight, take a right at the first intersection. At the next intersection, there should be an old-fashioned store to the left. There is also a dinosaur mural to the right, and Touchdown is on the back of the dinosaur. So we see these two parts of navigating to a specific location and then finding the location of Touchdown that is not visible in the environment. So what we need to do is we need to get the follower to click on a specific pixel in the environment in order to guess where Touchdown is located, given the description. So following this kind of instruction, the instructor starts by turning around and then going until the next intersection where it will take right. And you can see how complex is the environment and how dynamic and the amount of movement it includes. Then after turning right, the follower continues until the junction where it sees this bar on the left, which looks somewhat like an old-fashioned store. It switches to the part where it's identified the location of Touchdown, clicks on a pixel in the environment to find the hidden teddy bear. This kind of formulation allows for multiple tasks that we can where we can decompose into two tasks, like navigation only, given an instruction and a starting point, navigate to the goal position, and spatial description resolution, or what we also refer to as SDR, where giving a sentence and a specific panorama, you need to find the location of Touchdown. So without any navigation, or doing the complete task together, navigate first to the goal and then find a Touchdown. For data collection, we use the sequence of 4 tasks on a Mechanical Turk: writing, propagation, validation, and segmentation. The leader instruction writing during the first instruction task is tied immediately to a measurable execution by the follower in the validation, which is extremely easy to validate because it entails finding the location of Touchdown. And all of it is done using a customized Street View environment on top of a Street View's API. So in the first task, in the writing task, we ask instructors not to refer to text and images, number or street names, and we randomly end set the goal position to the middle of a block. This requires relying on spatial descriptions rather than simply counting blocks or intersections. So the way it starts is that the instructor sees an overhead view with the path, including the starting position and the goal, and they are instructed to write an instruction only relying on the panoramic view. As they navigate in the environment, they write an instruction, and once they get to the goal position, they switch to a mode where they select a place to put touchdown, and describe and write in the description where they placed a touchdown. Once we complete the writing task, the second task is propagation. So we want to allow some slack in what is the correct navigation goal, because the instructions are often ambiguous with regard to a specific panorama. So what we do is we propagate the location of touchdown to neighboring panoramas from which the location of the teddy bear is not occluded, so it's visible. And we do this using another task by showing workers the original panorama where touchdown is placed, and showing them a neighboring panorama and asking them to place touchdown in this neighboring panorama. Given this propagated location of touchdown and the instruction, and that we have a starting goal, what we can do is we can do validation. We ask followers, so different workers, to basically start from the start position, follow the instructions, and find touchdown by clicking on a position in the environment. Task completion is extremely easy to verify because it just simply requires finding touchdown. And once they complete the task successfully, we give bonus both to the original instruction writer and the follower, which really aligns the incentives of the workers with our goal of collecting this kind of like very task-oriented, or intent-oriented, if you would like, natural language data. Finally, we want to create two tasks from touchdown. So we want to be able to solve navigation and the spatial description resolution task independently. So we have a segmentation task where we ask workers to highlight the parts of the text that are for navigation and for SDR, and these may overlap. So what do we get? We had over 200 people work as instruction writers and validators, and we collected over 9,000 of these examples, and we split them to train, dev, and test set. This is a relatively small data set by the scale of a contemporary data set, and this is intentional because one of the key challenges is to deal with a complex environment given relatively limited amount of instruction data, but a lot of visual data. We can analyze this data and see how it compares to other contemporary data sets. So on average, the length of the texts are very long, almost 110 tokens. Compared to room, the navigation part is much longer, about 90 tokens compared to about 30 tokens. Room-to-room paths are also much shorter. If we look at the last bullet here, we see that paths in touchdown are about 35 panoramas compared to 6 in room-to-room. This is different in other more recent data set like room across room, where the paths are much longer, and as expected, the instructions, or the text itself, the instructions, are also much longer. For SDR, the most relevant comparison is referring expression resolution. Whereas in SDR texts are about 30 tokens, it's much longer than what we see in Google RefX, where we have 8.5 tokens on average, and the referred game where we have 4.4 tokens on average. In general, because of the more complex and rich environments, we have a much larger vocabulary in touchdown compared to room-to-room, about 5,600 compared to around 3,100. We also did a more in-depth language analysis by qualitatively analyzing sampled examples from a touchdown and compared it to instructions from room-to-room. So we analyzed for 11 semantic categories, and we report mean of instances per example. There is much more analysis in the paper. This kind of analysis, we first introduced it when we designed the NLVR task, Natural Language Visual Reasoning, and it was later adopted in other recent datasets for visual language, including NLVR2, Room Across Room, and Refer 360. So for the language analysis, but compared to room, there is this confounding factor that room-to-room instructions are much shorter, but in general we see a significant high representation of very interesting semantic phenomena, including references to entities, a lot more spatial relations, especially a significant growth in allocentric spatial relations. In these more complex environments where there is a lot of density of objects, we tend to use descriptions that are looking at the relations of objects to one another without dependence on the agent's current location. We see a lot of temporal conditions, state verifications, and a lot of co-references. Okay, just to give you a quick idea of like the performance of contemporary models on the two tasks, on SDR and navigation, I just want to show you some baseline and talk very briefly about evaluations for these tasks. So for SDR, the goal is to identify the location of touchdown given a panorama. So we give a panorama, we want to basically click on the pixel, select the pixel where touchdown is located. For evaluation, we use 3 measures. So we can measure accuracy by predicting the position close enough to the goal position, and the threshold we use is 80 pixels. We can measure consistency because of how the data was collected, and we actually propagated the location of touchdown to neighboring panoramas. We can get a point only if we solve all the propagated panoramas for the same SDR text correctly. So this really allows us to see that the models are more robust to changes in perspectives. And we can also measure the mean distance error. So given that you selected the pixel, how close you are to the goal position. And in general, models leave a lot of room for improvement. The best current result for this model is using a model called LingoNet, which is a language conditioned unit architecture. It gives you about almost 35% accuracy, but a significant drop in consistency, showing that the model is still not very robust to changes in perspective, and this leaves a lot of room for improvement. Just to give you an idea of the kind of thing that the LingoNet model solves well. So given this kind of phrase where touchdown is on the top of the staircase, LingoNet is able to solve it correctly, and we can see that and it's able to identify the staircase and locate touchdown on top of it. In this environment, there are no other visible staircase, so the ambiguity is relatively limited. However, in this complex example, where the location of touchdown is relatively to a doorway, LingoNet fails, and it actually identifies and puts the probability. So the correct solution is here, the correct location. But what LingoNet does is actually distributes the probability distribution across all kind of doors it sees in the environment, and it shows that it's really unable to really account for the full compositionality in language. For the navigation task, our goal is just to follow these navigation instructions by moving through the environment from the starting position to the goal and reaching the goal panorama. This does not include the SDR task. So as you can see in this example, the SDR phrase is segmented out. It does not appear as part of the text. For evaluation, we use 2 measures, although more recent papers are reporting more of the common metrics that you see in VLN. We use accuracy, which basically is like requiring you to stop at the annotated goal panorama or one of the propagated panoramas that are nearby. And we use success weighted by edit distance, and this which we introduced with the touchdown task. This measure basically measures the edit distance between the correct, the reference path, and the prediction, and then weighs the success measure by this distance. So the closer the edge is the correct execution, success is considered better. And in this, in general for navigation, there is a lot of room for improvement, and even when you use transformers plus pre-training plus augmentations, you see some improvement over more or simpler baselines, a significant improvement of about 4 points along both task completion and ASCD, but still leaving a lot of room for improvement and to forge ahead. Okay, so to get touchdown, you can download the panoramas by requesting the StreetLearn environment from this website, and then you can download the language demonstration data from this GitHub repository. Before we conclude, I want to very quickly go over some related tasks and give you some pointers if you're interested. So the SDR task has been followed up more recently by a resource for solving SDR in indoor panoramas in the Refer 360 dataset. There are a number of works that use panoramas for navigation with language and dialogue, or with synthetic instructions, the kind you get from Google Maps, or even without language using goal specifications or landmark navigation. Okay, so this concludes the first part where we focus on real-life observations, and now let's switch to talk about real-life control of physical agents. The task that we are focused on is navigation between landmarks with a quadcopter drone. We use an internal aero quadcopter. This is the drone that we see here on the right. It observes a first-person RGB camera image from the camera here, and it also has access to 6 degrees of freedom pose estimates that give us its position in 3D space. The focus of this section is on the model design that is required in order to get this drone to follow instruction while continuously moving in the environment and observing it. And the main takeaway that I want you to take away from this model design is how we build the model so it can accumulate observations and reason spatially about the space around it and ground it to the language. This is the environment that we are using, an example instance of the environment with an example instruction. It's a roughly 5 by 5 meter cage where the drone is navigating between landmarks. The landmarks are sampled from a larger set of landmarks and randomly placed for every instruction, so every environment is different. The instruction here, for example, is after the blue bale, take a right towards the small white bush. Before the white bush, take a right and head towards the right side of the banana. What the drone observes is this first-person observation. It doesn't have access to this overhead view of the environment. And as we can see, one key problem already from the starting position is partial observability. The drone doesn't observe this white bush, that is this very weird way to refer to this large stone that is here, or the banana that indicates where its goal position is. Instead, it will observe them as it flies through the environment and follow the instruction, and it will do this by seeing them in a diverse set of perspectives and observations where landmarks are coming in and out of its field of view. And the rollout that I'm showing here is the output of the model and the learning approach that I will describe in the rest of this section. More formally, the drone maintains a configuration of target velocities. This configuration is a pair of two real numbers, a linear forward velocity and an angular yaw rate. Each action that the model takes updates the configuration or takes the stop action, which brings the drone to a stop and indicates that it's completed the instruction. Below this configuration is fed into a low-level controller that controls the voltage of the 4 motors. Our goal is to learn a mapping from our inputs, the natural language instruction, the pose estimates, and the RGB input from the camera into these configuration updates. So we continuously run this function and continuously outputs new configuration updates, so these two real numbers, until we reach the goal position, and then the drone needs to output the stop action to indicate it completed the instruction and come to a halt. So this problem of controlling the drone, even including natural language, has been studied in robotics, even if not very extensively. And usually the way it's done in robotics is by decomposing this very complex problem into separate components, which are built or trained separately. So you can think about having a component for perception, for mapping, planning, language understanding, and control. And this usually entails designing some kind of an API that bridges all these components together, often using this symbolic meaning representation that is designed for the language. This scaling up this symbolic representation is extremely challenging, especially for complex real-life environments. And integrating all these parts together requires a relatively complex engineering process for integration that is extremely difficult to scale. So what we propose instead, instead we take a very much a more learning-based approach, where the goal is to learn a single model that maps directly from the inputs, the instructions, the RGB inputs from the camera and the pose estimates, all the way into these configuration updates, so these two real numbers or the stop action. And one of the key questions that we think about as we design this model is how can we rethink modularity and interpretability when we pack everything into a single model? So modularity gives you a lot of advantages, but it's very difficult to scale. It requires a lot of manual design of representations. On the other hand, these approaches leave much for learning, so there is a lot of flexibility. So the question remains, how can we bring back some of the ideas of modularity and the interpretability it allows into these kind of like more learning models in order to learn from fewer samples and even allow users to peer into the model and understand its reasoning. So what we propose, what we do is we design a single model that is a single neural network base divided into two stages with interpretable intermediate representations. In the first stage, we predict states that we are likely to visit and track accumulated observability. This means that we generate this visitation distribution, which I'll define more formally in a minute, and this observability mask of what parts of the environment we have observed. Given these two intermediate representations, in the second stage, we generate actions to visit high probability states and explore the environment, and at the end, stop at the goal position. So what are these visitation distributions? So a state visitation distribution, D, is a distribution over states in the environment, or in our case, positions, that is conditioned over a policy pi and a start at S0. Basically, following a specific policy and starting a specific state as S0, how much of the execution, what's the probability you're going to visit each of the states? So predicting this visitation distribution D for an expert policy pi star tells us the states to visit to complete the task given this Oracle expert policy. Of course, we don't have access to this expert policy, but what we would like is to be able to predict it as close as predict the distribution as close as possible to this pi star that we don't have access to. In practice, we compute two of these distributions, a trajectory visitation distribution and a goal visitation distribution. This distribution can be treated as reflecting the agent plan, and we can actually visualize them by superimposing them over an overhead view of the environment, which the agent doesn't have access to, but allows us to see what's the reasoning that is happening inside the neural network in this intermediate representation. We have these two distributions. The trajectory probability tells us the position that we are likely to visit as we fly through the environment, and it's marked here in red. And the goal probability tells us the probability to take the stop action in a specific position, and it's marked here in green. For the goal probability, we are also modeling we're also adding an additional event, which is the unobserved goal event. So if we don't observe the goal, we want the agent to put the probability mass not on positions in the environment, that because we haven't observed the correct goal distribution yet. We want instead to put it on this placeholder event that is visualized here using this green bar. And these distributions are constantly refined as we observe more and more of the environment. So as you can see here in the beginning where we are facing in this direction and we don't really see the goal position, what the agent does is it puts most of the goal probability on this unobserved goal event, and the green bar is almost full. As it flies through the environment and observes the environment and identifies the goal position, it shifts the probability mass from this unobserved goal event to positions in the environment and slowly localizes to more and more specific position to take the stop action. So in this first stage, where we are generating this visitation distribution, we have this mapping process where we generate two learned maps of the environment. So given an instruction and a first-person observation and the pose estimates, we generate ResNet-based features. This is a small ResNet architecture that is learned from scratch for this task. And we feed these three inputs into a mapping procedure that generates two types of maps of the environment. And this process is done using 4 steps. And during this process, we also deterministically accumulate what parts of the environment we observed. So in the first step, we use the ResNet architecture to extract features from the first-person view, so basically from the camera view. This basically recovers a low-resolution semantic view of the environment where the spatial relations between objects are retained in each of these feature maps. So for example, for the house, we will have features that are concentrated around the same area in the feature map that we recover from the ResNet. As we move through the environment, we see that the first-person view shifts, and so are the features for the house, and new objects enter into the environment, and their features are located at the right place in the first-person view. In the second step, we take this feature map and we use a deterministic projection using a pinhole camera model to project from this first-person view to a global view of the environment, to basically project it to the ground. We can do this because we have the properties of the camera and we have access to the pose estimates of the drone. So using a very simple pinhole camera model, we can transform from the first-person view to a third-person view, where it's just a projection of the same features we get in this feature map from the first-person view. We then accumulate using, again, a deterministic process these features over time to create the first of the two maps we construct. This is a semantic map of the environment. So as we get projected features that we compute from the first-person view, we use a leaky integrator to create the semantic map. At each time step, we take the previous semantic map and integrate it with the new projected features to gradually construct a semantic map of the entire environment. In essence, this provides the agent with a sort of memory, a spatial memory of what has been observed in an environment, so it can reason about it even if it doesn't see an object in its first-person view at this point. But this process is completely deterministic, so it doesn't really entail learning a complex reasoning of constructing this map. In the fourth step, we incorporate the text into the semantic map to create a grounding map. The intention of this map is to focus on elements in the semantic map that the text is referring to. And we do this in a very simple way. We take the text, we recover a vector representation of it, and then we create from this vector representation a one-by-one convolutional filter that we convolve over the semantic map, basically filtering it to get the grounding map. These two maps are both computed in the global reference frame, so in the coordinate system of the environment, and we can visualize them by superimposing them on this overhead view of the environment that the agent doesn't have access to. At the same time, because again using the properties of the camera and the pose estimates of the drone, we can also accumulate the observation mask using a very similar process with a leaky integrator that integrates over time to get deterministically accumulate an observation mask of the environment. So this process allows us to recover this differentiable mapping process allows us using a relatively simple process that includes getting learned ResNet features that are learned for the task, and the deterministic projection process to get these two types of maps and the observability mask. Given giving these maps, what we do is we use an architecture called LingoNet in order to predict the two visitation distributions over that are predicted over the maps themselves. So the way we do it is we compute two distributions, a trajectory visitation and goal visitation distributions. And we cast this process as an image generation process, where we think about these two distributions as generating a two-channel image where each of the channels is normalized. So LingoNet is an image-to-image encoder-decoder architecture. So given an image, which is our semantic maps, with multiple channels for all the semantic properties that they capture, it generates a two-channel image that are these distributions, and these the input and the output images are exactly in the same dimensions. LingoNet is based on the unit architecture, but is modified in order to be language conditioned, and it allows visual reasoning at multiple image scales that are conditioned on the language at all levels of reasoning using text-based convolution. And if you remember, just in the previous part, we discussed how we can apply LingoNet to the SDR task, to do spatial description resolution, where it's currently provides the state-of-the-art results. So just to give you a quick idea of how LingoNet is structured, we have the semantic maps that we are getting as input here. They're going through a series of convolutions that generate feature maps of coarser resolution, or if you would like, lower and lower resolutions through a number of levels. It takes the instruction, and given an RNN computed representation of the instruction, it creates a number of text kernels. Each of these text kernels is used for one of the levels in the LingoNet hierarchy, and it's used to convolve over these computed feature maps, and finally given the output from the text convolutions, we deconvolve from the bottom to the top to create feature maps of higher and higher resolution, until at the end we compute two channels, one for each of the distributions. We push each of them independently for a softmax to compute our visitation distributions. Okay, so this describes the first stage of the process. The second stage is much simpler. It's the stage where we take this visitation distribution and the observability mask, and we want to compute the action to take. Given that we computed this intermediate representation, we are left with a relatively simple control problem without a language that doesn't really need to reason about the raw observations or the language. So what we do is we transform and crop the observability mask and the visitation distributions, and then use a very simple control network that includes a number of CNNs and an MLP in order to output a configuration update, so two real numbers, or take the stop action. In general, the advantage of these intermediate representations is that they leave they create a control problem that is detached from the complex inputs, both the language and the raw observations, and leaves us with a relatively simple spatial reasoning problem. As you can see, the velocities that we need to take are relatively easy to compute once you get this very focused and local view of the visitation distributions. Okay, so one important aspect to emphasize, to take away from this architecture is the balance between learning and engineering that it adopts. So there are a number of so the architecture is designed to learn what we are actually pretty good at learning. So we can learn visual features using the ResNet architecture. We can learn the text representation. We can learn the image generation process using the LingoNet architecture in order to generate the visitation distributions. And finally, we learn how to solve the control problem using the control network. All these things are problems that are really difficult to solve using engineering solutions, but we have a pretty good idea of how to learn them. On the other hand, there are several problems that this architecture addresses that are extremely difficult to learn using a neural architecture, including feature projection, for which we use a pinhole camera model, map accumulation, for which we use a leaky integrator, and the egocentric transformations that happen before the control network that are done using very simple matrix rotation. And this control network, and the nice thing that this complete network remains fully differentiable. So although we have a number of engineered components, they're all done using relatively simple algebraic operations that are fully differentiable. We train our model by taking advantage of simulation, a common practice in robotics in recent years. Rather than training in simulation and then having a separate domain adaptation problem in order to move the model to the real world, we jointly train in both environments. But we do it without access to any autonomous flight during learning in the real environment, in the physical environment, instead only assuming access to a small amount of demonstration data. So our data between the environment is different. In the simulator we have access to demonstrations, but also the ability to fly the drone and observe how it behaves and how it moves through the environment. In the physical environment, on the other hand, we only have a small amount of demonstration data without the ability for autonomous flight, which will be both costly and unsafe. Due to the limited amount of time we have, I am not able to describe the algorithm in detail. The learning process we use is called SURREAL, Supervised and Reinforcement Asynchronous Learning. The first stage of the network is trained using supervised learning, and the second stage using reinforcement learning, with an intrinsic reward that simply encourages it to follow the visitation distribution given for the first stage. These two processes run at the same time asynchronously and constantly exchange parameters and sampled action sequences that are then considered as demonstrations. One key important aspect is to jointly learn in both environments. In the supervised learning, we have two CNNs, one for the real environments and one for the simulated environment, and we use an adversarial loss to make sure that the features that come out of those CNNs are invariant depending on the environment that they are coming from. This allows us to train our model to jointly work in both environments without any autonomous flight during learning in the real environment. For our experiments, we use an Intel Aero quadcopter, a Vicon motion capturing system for pose estimate, AirSync for simulation, and roughly 1.5% of the training data is in the physical environment, so 400 examples versus 23,000 in the simulation. So we really don't need that much demonstrations in the physical environments for effective learning. Our focus is human evaluation because it's only for human evaluation that we accurately capture the semantics of the instruction to see if the execution is correct. We ask people to evaluate examples on a 5-point Likert scale according to did you get the goal right or did you get the path including reaching the goal right, so the more challenging evaluation. I'm showing here 5 systems. The first one, average, is a non-learning baseline where you simply move for the model moves for the average amount of time with the average velocity, and not surprisingly it's doing pretty bad. So this is a Gantt chart. It shows the distribution over Likert scores. The next one, PVN-BC, so PVN stands for Position Visitation Network. It's a variant of our model that doesn't include modeling of observability, trained with behavior cloning or supervised learning. This system does significantly better than the average baseline. It's not surprised. Our model, Position Visitation Network version 2 or PVN2, trained with supervised learning, that's the next system, does just about the same or even actually worse than the more primitive model. So the bells and whistles with supervised learning are not actually helping, but even hurting. We see significantly more ones for path score. When we add our learning algorithm, SURREAL, with the RL component, we see a significant improvement in performance. So the model, our model receives 5-point path scores 40% of the time, which is a 25% improvement over the next baseline, so which is PVN2 behavior cloning. So this shows that the improvement of all the new bells and whistles in the models really benefit from the introduction of reinforcement learning into the learning problem and the different awards that are integrated in it. Finally, there is an Oracle performance is significantly better than our systems, showing that there is still much room for improvement. Look at the single examples that highlight some of the reasoning that the reinforcement learning process allows the system to acquire. So in this example, the drone follows the instruction: once near the rear of the gorilla, turn right and head towards the rock, stopping once near it. The drone is positioned here and it's facing in this direction. I'm also visualizing the overhead view at the bottom right, and you can see that the drone is facing in this direction. From its starting position, you will notice that the drone does not observe the final position, the goal position, which is here, and it correctly reasons about it and puts up most of the probability mass of the goal distribution on the unobserved goal event here. If you focus on the instruction, you will also notice that the instruction is a bit odd, and indeed it reflects an error that the instruction writer made during the data collection process. While we want the drone to turn left and head towards this to this position, the instruction writer confused the directions and asked the drone to turn right. As our drone executes this instruction, what it does, it actually follows the instruction, but then it quickly corrects itself because it reasons that it does not observe the goal, does this sweeping motion of the environment, identifies the correct goal position, moves the unobserved goal event, the probability mass that is on the unobserved goal event, to positions in the environment, and flies and stops at the correct position. And this is a behavior that we do not see in the training data and is completely acquired from the RL process and the experiments in the simulated environment. Okay, so I'm going to conclude now and pass the presentation to Peter Anderson, that will talk about how we can use the kind of reasoning that we learn in environments that are made out of 3D scans, like Matterport 3D, in order to navigate in physical buildings.
Thanks, Yoav. My name is Peter Anderson. I'm a research scientist at Google, and I'll be presenting the third case study from 3D scans to physical buildings. So our goal in this work is to take a VLN agent trained in simulation on the room-to-room or R2R dataset, which, as you recall, is based on a navigation graph, as shown here, and to transfer this agent to a robot. And we'll be using a TotalBot. And this particular TotalBot we've equipped with a consumer-grade 360-degree camera in some effort to reduce some of the domain differences between the Matterport training data and the experience of the robot. We've mounted this camera about 1.3 meters above the ground, which is similar to a Matterport camera on a tripod. And the robot's also equipped with a laser scanner and a forward-facing RGBD camera, which is used for obstacle avoidance. So what we'll be doing here is looking at a parallel evaluation using sim and real environments, both of them previously unseen, so not seen in training. The real environment is a 325 square meter space at Georgia Tech, as you can see in the floor plan here. The simulator environment is the Matterport 3D camera reconstruction of this environment, on top of which we've annotated a navigation graph similar to the room-to-room dataset. So as you can see, one of the first challenges that will arise, let's call it challenge 1, will be differences in the action space. As you can imagine, low-level control of a physical robot is very, very different to the simulator action, which basically involves selecting which one of these neighboring nodes in the graph the agent would like to teleport to. The other fairly significant difference between the sim and real settings is the visual observations. So as you can see on the left, the robot camera is a consumer-grade camera, and visually it looks quite different to the Matterport camera, which is shown on the right, which is much more expensive and has a much higher dynamic range. So this is, if you like, the second challenge, overcoming these visual domain differences. With regards to the navigation instructions that the agents will be following, these are the same in both the sim and the real settings. In both cases, it's the same set of 111 crowdsourced navigation instructions. These were collected using the same user interface as the room-to-room dataset, using workers from Amazon Mechanical Turk. And so these should be as similar as possible to the training data in R2R. You can see some examples here. With regards to evaluation, we'll be using the standard path fidelity metrics like success rate and NTDW, which evaluates the similarity of two trajectories. And our main aim here will be to quantify the sim to real gap. So as you can see in this example here, we've plotted 4 different runs on top of this floor plan, 2 in the simulator and 2 on the robot. And basically what we're interested in seeing is, does the agent follow the same path in the real world as it does in the sim, and what's the performance overall? And of course, how large is that gap? Oh, but one problem here. How do we actually know where the robot is? Well, to solve that problem, we actually run a completely separate, isolated second navigation stack on the robot. And this navigation stack is given a occupancy map. So as you can see here, we've collected a 5 centimeter resolution occupancy map in advance, and we use that along with this second navigation stack to keep track of the robot's actual location for the purpose of evaluation. In the simulator, of course, keeping track of where the robot is no problem. Right, so let's look at the approach. The standard actions of the agent in the VLN simulator look something like this. The simulator generates an RGB panoramic image, which is consumed by the VLN agent. The agent is also provided by the simulator a set of adjacent nodes in the navigation graph. And basically, all the agent needs to do is select which of these adjacent nodes it would like to move to, and the navigation is performed perfectly. The agent arrives at the new position or new pose, and this process repeats. So how will this work on the robot? In the first instance, with regards to the visual observations, we can use the robot's camera to provide a similar RGB panorama to the simulator. But the question then arises, how do we mock or otherwise provide the VLN agent with these adjacent navigation graph nodes? And to do that, we're going to propose a new module called a subgoal module, which will basically try to replicate the same API as the navigation graph by predicting nearby positions that would make good subgoals or good, equivalent short-term navigation positions. And in order to do that, the subgoal module will use the RGB panorama as well as the output of the laser scanner. Having done that, the VLN agent can select which of these subgoals it intends to move to, and to actually implement that motion, we use standard ROS or robot operating system components, such as move base and G mapping to perform SLAM and to navigate to the next position. So the overall approach here is to try to provide the VLN agent with a similar API to what it was trained on in the simulator, and to basically try to make use of existing and well-tested ROS components for navigation and movement. A little bit more detail about the subgoal module. As you can see here, it takes as input this laser scan and the CNN features from the panoramic image. It's effectively a UNet style architecture, and it makes predictions about the most likely subgoal positions in a radial occupancy map with range and heading as shown at the bottom left. And in order to do so, we've trained it on the Matterport 3D and R2R navigation graphs. So let's have a look at how this all works on the actual robot. So what we're looking at here is at top left, the robot's forward-facing camera. At bottom left is the panoramic camera for the robot, which only fires periodically. At the very bottom is the instruction that the robot's attempting to follow. At the top right, you can see a third-person view as the robot is moving through this environment. And then, of course, there's the map that indicates where the robot is, and in the green box, the goal that it's aiming towards. And so I want to point out that this is an easy setting here. So we've called this the with map setting because we actually provided the navigation graph to the robot up front. Okay, you can see a second example here. The robot is navigating, and you can see that the map is already populated with the complete navigation graph and occupancy grid. So this is an in-between setting. This doesn't help with any of the language grounding aspects, but what it does do is eliminate the action space differences between the simulator and the real world. It's worth considering, I guess, that for a robot to operate in the same environment for a period of time, it's not overly difficult to collect an occupancy map and even the navigation graph in advance. But this is not the full difficulty setting. So now we'll move to an example without any map at all. And when you look at the map here, you can see it starts empty. And then as the robot begins moving, it's gradually building up an occupancy map using the LiDAR. And it's also making predictions using the subgoal module about where the neighboring viewpoints or neighboring navigation graph nodes are that the robot can move to. And what you'll see in these examples is that this is much more challenging, and the robot is certainly less successful without any map initialization whatsoever. So let's have a look at some results over the entire set of 111 navigation instructions. So first of all, in the simulator, the agent achieves a success rate of about 56%, which is not too bad and similar to the room-to-room data set for this particular agent, which is based on the environmental dropout approach. One thing we can do here to test the visual domain differences is to still use the simulator, but simply replace the images. Instead of using the Matterport camera, we can replace the images with images from the theta camera used on the robot. And that causes the success rate to drop by about 6%. Fortunately, though, we can actually claw back some of that drop. And in this case, we've used domain randomization in the image space during training to mitigate some of that of those domain differences. And so this reduces the gap when using the images from the robot. But what about running this on the actual robot itself? So here's the first experiment in the with map setting. So this is equivalent to the first demo. And surprisingly, the sim to real gap here is actually perhaps smaller than expected, only about 5%. And so what this suggests is that the language groundings that were learned in simulation are successfully transferred to this unseen physical environment. But when we rely on the subgoal module and we initialize the map as completely empty with no navigation graph, in this case, the performance is very, very poor, and this is quite devastating for the sim to real gap. And so the conclusion here really is that reliance on this navigation graph is a very significant barrier to sim to real transfer for VLN. And I think this does motivate perhaps the further use and investigation of continuous simulators such as Habitat. So there's some nice work done in that regard by Jacob Krantz and collaborators such as VLN CE, which is a port of the room-to-room dataset to Habitat, and of course the RXR Habitat Challenge, as you see here, which is a port of the RXR dataset to Habitat. Thank you very much, and I hope you've enjoyed our tutorial.